All right, recording's back rolling. We're a good few minutes in class. You guys have been working on this a while, so I want to throw some hits to you guys, show you guys how to think about this puzzle, how to frame it, make sure you guys are on the right track here. So this is going to be a puzzle in two parts. The first part is the ball rolls down the incline, and the second part it turns out, guys, when it leaves the incline, it turns into what right here. This is a what? Starts with a P. Ooh, I heard projectile and I heard parabola, and those are both right. It was start with P. They both right. Yeah, it's a projectile that follows a parabola path. Yeah. Okay. So that goes way back in this class, doesn't it? Okay. So here's something we've been doing last week or two, and here's something that we did like way back in the beginning. Okay. So you got to put those two parts together. So this ball rolling to the bottom. Well, what kind of ball is this? Because different balls are rolled differently. Okay. Like here's a basketball. If you thought it was pretty close to a spherical shell, it might work out like this. Uh, now, this is with the energy method. I showed you guys there's also a torque method to solve it. Of course, it gives you the same answer. I think it's the easier way to solve it. Okay. So if that was a basketball, maybe it would work about like this. Here's a general ball. Right? That could be anything. So I have some general I here. Okay. And then I got a solid ball. Here's a solid ball, how that rolls down. Right. Do you guys notice every single one of these, the mass and radius of the ball cancel out? All right, so maybe that could be a little helpful. Right. Of course, you could get mass and radius work up from there. Where is it? Here's what I'm looking for. So, see a racquetball. It's probably some version of a spherical shell, but I bet it has really thick skin on it. So maybe, do you guys think you could maybe interpolate between these two? Right? It's probably like on a scale. Right? Like if you solve this whole puzzle as if it was a spherical shell, the ball would land somewhere. If you solve the whole puzzle as if it was a solid sphere, the ball would land in a slightly different location. Do you think that this ball is probably somewhere between those two landing locations? Right. I'm just throwing some thoughts out there. Right. Right. All right. So once you figure out how fast it's going at the bottom, because that's what this is set up to solve, right? The linear speed at the bottom. Right. Now you can treat this like a projectile. Right. So here's a projectile poster I have from back in the day. Now this is not exactly what you have, but I'm going to start with this, and then we'll consider the complications from this. Right. So this was a lab you guys did. You guys remember those launchers launched off the balcony? Right, those little bouncy balls for spot where it lands. Okay. Let's think how projectiles work. I'm going way back, do a little review here. Okay. So if you want to spot where the ball lands, which is kind of what you guys are trying to figure out, okay, that's going to depend on how fast it's going, and also, also the height of the cliff, right? It like if you know how fast it's going across, does the horizontal component of velocity stay constant all the way across? It does. So then you can figure out where it lands only if you know how much time it's been falling for. But how much time it falls for, is that going to be from horizontal motion or from vertical motion? It's from vertical, right? So maybe somebody like, would it be true if that lab table was really short? It wouldn't be in the air for very long, probably land pretty close. But if the lab table was really tall, now it's in the air for a long time, now it's going to land further away. Right? So by the time you get to the projectile, maybe I'll start with the vertical stuff and then work from there. Okay? Now, how is the puzzle that you guys are trying to solve right now for zebra cakes different than the balcony launcher lab that you guys did last semester? Yeah. Yeah. Because the initial velocity is not straight horizontal on this puzzle, is it? See how it's going on an angle. Ooh. Do you guys think that the angle it's headed towards straight down matches this angle that it's rolling from? Yeah, like right when it's leaving the edge, however many degrees this is. I bet you could have a velocity vector that goes about like this, and you could split it into components and say what's the horizontal component and what's the vertical component of that velocity right as it's leaving the edge. Okay. Now, speaking of those components, let's do it one by one. The horizontal component, like whatever the speed is, suppose you get like, I don't know, 11 meters per second. I don't think it's correct, but I'm just making up a number. So many meters per second for the total speed it's leaving the edge. Okay. If you want to know the horizontal component, do you take that total speed times sine or cosine of this angle? Cosine. Yeah. And if you want to know the vertical component, as if you took the ball and were throwing it straight down, because it would be the same as that if I'm just looking at strictly vertical, that would be the total speed times what? Sine of this angle. Yeah. Right, you guys see that? Right, so you got your sine and cosine components. Right? And then I got to figure out how much time it takes to reach the ground so that I can after switch over to horizontal and say how far away does it land. Okay? Now the time, you cannot just use, oh, h equals 1/2 gt squared, because this is assuming that either you drop it or you threw it horizontally, so that there's zero initial vertical component velocity, right? Which is not the case for this one. This one, there is a initial vertical component of velocity, right? So let's go back to kinematic, right? Or your kinematic equations. Here's your kinematic equations. Guys, which of these equations allows you to solve for a time given some height change? And there's only one that will allow you to do that. A time with a height change. Which one is it? Let's see. Well, let's go bottom to top here. Guys, does the bottom one say anything about time? Okay, so there's no time to solve for, so it's probably not that one. Is it the second one? The second one doesn't say anything about displacements, so I don't have a place to plug in a height for the lab table. Okay. How about the first one? Can you use the first one? Okay. Oh, guys, what does this variable represent in what you're solving today? Yeah, the height of the lab table. There's the height of the lab table. It's some displacement, height of the lab table, right? This V naught is really V naught in the y direction, right? Because we're setting up a vertical equation. By the time you get to this part in your solution, this is really going to be strictly vertical. What is the ball doing vertically? So this is V naught y. That's your total speed times sine theta. Okay. Ooh, guys, what are you plugging in for this A right here? 9.8 meters per second squared, right? And if you use 9.8 in your calculator, make sure everything's in meters and seconds, right, as you're calculating. If you have everything in base SI units, it's probably a safe way to go, right? And you're solving for this T. Oh boy. Guys, if you're solving for this T, and see it's being squared here, it's not squared here, there's some height over here. How do you extract the T? You have to apply the what? Quadratic. Yeah. Can you guys set up a quadratic equation? Sometime? Okay. So let's put this all together. They go back to the beginning picture. You guys solve it. Okay. So you can use rotational dynamics to solve the ball rolling down the incline, figure out how fast does it leave the edge. Maybe you have to make some reasonable assumptions or find some boundary conditions. Okay. Then you split that into components, saying what is it doing horizontally, what is it doing vertically. That vertical motion combined with the height of the lab table, you can determine how much time it takes to reach the floor. And there's going to be a quadratic equation involved along the way. Once you get that time, you do the calculator, get so many, it's probably a fraction of a second, right? If you get a fraction of a second, you're probably on the right track, right? Then take the horizontal component of velocity, so v cosine theta, multiply by the time, you can spot exactly where the ball lands. Right? I'm also working on this solution myself off screen, and I will get that posted to Google Classroom after school today.